Hello all, my name is Ajay Shastry. I, on behalf of myself and my co-authors Ravi Teja, Professor Aditya Nigam and Professor Chetan Arora would like to present our work favoring one among equals, not a good idea, many to one matching for robust transformer-based pedestrian detection. Pedestrian detection is the task of localizing and classifying pedestrians on an image. Given an image as an input, our task is to localize on where the pedestrian is and draw a bounding box around it. It has its application in autonomous driving, surveillance, and robotic navigation. Detecting pedestrians of different sizes and of different occlusion level is very challenging. The pedestrians can be occluded by another pedestrian or by another object. When the pedestrians are occluded, most of its body parts are not clearly visible. There has been multiple works on pedestrian detection using the classical convolutional neural networks or CNNs. The CNN architectures make multiple predictions per pedestrian. So there is a need for a post-processing step to remove these duplicates, and NMS is one such post-processing step. NMS uses the overlap information between two bounding boxes to remove duplicates, and it backfires when there are two pedestrians very close to each other. Let us try to understand using an example. Imagine we have an image with two pedestrians very close by, and your network manages to make a prediction for both of them. But due to the NMS, since it uses the overlap information and these two bounding boxes are having a very high overlap, it erroneously removes one of them. In order to overcome the challenges of CNN based object detection networks, there has been transformer based object detection networks. And Dino is one such transformer based object detection network. Dino considers object detection as a set prediction task and does not predict duplicates. But when extended to the task of pedestrian detection, we see that its performance is not on par with its CNN counterparts. The below is the architecture for Dino, and let's try to understand its flow. The dyno takes an image as an input, passes it through a backbone to extract initial set of features, and it then passes it through a sequence of encoders to get an enhanced feature map as an output. These enhanced feature maps are then passed through a region proposal network to get initial region proposals, and these region proposals are used to initialize object queries. Dyno uses object queries to represent each object, and each query represents one single object. These queries are initialized using the region proposal, and then they are passed through a sequence of decoders. In the decoders, these queries extract features in and around that particular region proposal, and then we get enhanced queries as an output from the decoders. These enhanced queries are passed through an MLP to perform classification and regression, and then during the inference phase, a simple thresholding will help remove most of the duplicates and resulting in one prediction per pedestrian. In order to achieve this uh, feat of not predicting any duplicates, the whole transformer network is being trained using a Hungarian one-to-one matching algorithm, where it tries to match one prediction to the ground truth, and the network is trained in such a way that it does not predict duplicates. Our task is to understand the reason behind the failure, and our analysis revealed that the failure is because of this region proposal network. Dino uses object queries to represent each object, and queries are initialized using region proposals. Our analysis revealed that the poor initialization of these object queries are the reason behind the failure. Let us try to understand using an example. Assume the yellow color is the ground truth for the pedestrian and green color are the proposals generated by the existing network. We see that the proposals are not tight, are not does not clearly localize on the pedestrian, and if we use these proposals for the initialization purpose, then the quality of features extracted by those queries are not great, causing the network to fail. So our task is to improve these proposals so that the better features are extracted. Poor proposals are generated because of the undertraining of the region proposal network. Dino uses Hungarian algorithm to perform prediction to ground truth matching, and this Hungarian algorithm at the region proposal network is the reason for undertraining. Let's try to understand using an example. Let's assume that we had a pedestrian with a yellow color bounding box as its ground truth. Assume that there were four predictions which is marked in blue color. Let two of the bounding boxes completely cover or enclose the pedestrians, and there are two bounding boxes which is present at the outer periphery, or it does not cover the pedestrian completely. Now, when we assign the task of matching to an Hungarian algorithm, the Hungarian method generally creates a cost matrix which consists of the cost values between every proposal to every ground truth, and the Hungarian algorithm optimizes on this cost matrix to find such proposal with the minimum cost. And green color bounding box was the one that was matched to the ground truth with the least cost. Now we see that this ground green color bounding box receives a positive gradient, while there is another bounding box which exactly encloses this pedestrian, but it is getting a negative gradient. So because of which the performance of the region proposal network is poor. One simple trickery to increase the number of positive matches is to tweak the Hungarian algorithm in such a way that instead of performing one to one match, it performs many to one match. But this leads to incorrect matches. Let's try to understand using an example. Assume that yellow color box was the ground truth and the rest was the predictions, and now we had asked the network to perform three matches rather than one. Now see that there are three green color bounding boxes which got matched to the particular ground truth. Now we see that two of them are a good match and there is one bounding box that's a wrong match. Now we are sending a positive gradient for this wrong match and causing the hindrance in the network's training. So we need to have a methodology with which the ground truth and the predictions get matched if the quality of the predictions are good. So now when we pose the same scenario to our algorithm was able to match the good predictions to the ground truth, uh, discarding the rest. This is the architecture with the proposed flow-based matching. At the region proposal layer, instead of the Hungarian one-to-one matching, we are using the flow-based many-to-one matching. We pose the matching problem as a min-cost flow problem. Therefore, we construct a bipartite graph with queries on one side and ground truths on the other. And the edge connecting the queries to the ground truth has a cost value equal to the cost of matching that particular proposal or the query to that particular ground truth. On the ground truth side, we have another node called the dummy ground truth, which is connected to every proposals or queries with a weight equal to something known as a dummy weight. And during the min cost flow computation, if there are matches whose cost is greater than this particular dummy weight, then all those matches or queries get matched to this dummy ground truth rather than the actual ground truth, reducing the number of bad matches and thereby increasing the performance of the network. Let's try to visualize the impact of our matching algorithm at the region proposal layer. For the ground truth covered in this yellow bounding box, these green color bounding boxes are the proposals given out by the vanilla dyno that use the traditional Hungarian one-to-one matching. With the integration of our flow-based many-to-one matching, we are able to see that the region proposals are way more tighter and is able to localize on the pedestrian properly. Quantitatively, we see an average increase in the number of proposals per ground truth in comparison to that of the vanilla dyno. Let us try to perform a qualitative analysis to compare the performance of our model with the existing state of the art. The yellow color bounding boxes are the ground truths, the green color ones are the prediction, the red color ones are the mispredictions, the magenta ones are the false positive. We are able to observe that our model performs better in comparison to the existing works in the heavy occlusion scenario, and our model is able to detect objects of different sizes. You also observe that our model fails in the scenarios when the objects are really small. When we perform a quantitative analysis and compare the performance of our models on four different benchmark data set, Eurocity persons, city persons, TJU pedestrian traffic, and Caltech, we see that our model consistently performs better than the existing state of the art, giving out very less misrate in comparison to the rest. Thank you.